So today we are going to discuss renormalization. We've discussed aspects of this in a number of previous classes, and we also went through an example of renormalization in non-relativistic quantum mechanics, where many of the calculations were easier and so we compute everything. So today we're going to try to put together many of the ideas we've discussed so far in this course and discuss renormalization for a particular theory. Well, for today's lecture, our example will be phi cube theory. So the naive Lagrangian for phi cube theory, just if we take our Klein-Gordon Lagrangian and add an interaction term as 3 powers of the field. So based on what we've seen previously is, in general, if we want to use the LSD reduction formula in the form we wrote it down in lecture, we can't just pick an arbitrary, can't just add an arbitrary term to our Lagrangian. In general, we need to shift and rescale. To use the LSZ reduction formula, we need to shift to set the vacuum expectation value to 0 and rescale to make the form factor the IKX. And so after we do that, the Lagrangian takes the form. So we get a bunch of extra factors here. One factor called Z phi, multiplying the kinetic term. I've also renamed name things, so parameters are not the same. First and second equations. So we get an extra factor of z in front of each of the terms in our original Lagrangian. We also get a new term. It wasn't there before. Phi comes from the shift. In general, we'd also get a constant here too, but that doesn't affect physics. So so this is what we get. And we want to use this Lagrangian to do perturbation theory. And so it's useful to rewrite this in a new way. Write this as a free Lagrangian, just the Klein-Gordon Lagrangian, plus 2 other terms. We're going to write one term as interaction term, and another term called the counter term. So explicitly, L free is Klein-Gordon Lagrangian. The interaction Lagrangian is the phi cube term that we wanted to add. And the counter term is all the extra stuff we get that we didn't want to add, but we have to add. There's a whole bunch of terms in this counter term Lagrangian. We get kinetic term, coefficient z phi minus 1. Get a mass term, em minus 1. And we also get this Wi-Fi term. And so our original Lagrangian, which naively we'd expect depends on 2 physical parameters, m and g, now has a whole lot more parameters. It's got zg, z phi, zm, y, as well as the original m and g. So in order to make predictions, in order to connect this theory to experiment, we need to find some constraints on these parameters. Or another way to think about it is find some relationships between these parameters and experiments. So that's what we're going to do today. We're going to try to figure out how we can relate the parameters in this Lagrangian to the assumptions we made already in deriving our Feynman rules, particularly the assumptions for the LSE reduction formula. Those assumptions are not going to be enough to uniquely determine these parameters. We're going to need to make some additional assumptions about the relationship between these parameters and experiments. So we'll use LSZ assumptions plus new assumptions about the relationship of the experiment of experiments to determine our parameters, the z's, y's, also have m and g. That's what we want to do. And we have to do this. We can't make predictions if we don't do that. There's no priori relationship between what I've written down here and an experiment. Okay, so that's where we're trying to go. And well, we already know something about some of these parameters. We know that in the limit g goes to 0, we should recover free Klein-Gordon theory. All these terms should go away. We should just get the free Klein-Gordon theory. The limit g goes to 0. So that tells us that we expect y, this term should just go away, that limit. Y should be 0 plus something that's order g. We also expect...
Is this a new assumption?
This is what we expect if the g goes to 0 limit.
These are not new assumptions, right? These are just the LSE assumptions?
We will write down some new assumptions later.
I thought these were new assumptions.
This is an expectation. If g goes to 0 gives us Klein-Gordon, then y should be 0 plus some correction. And in general, we won't be able to find an exact formula for y at all orders. We'll be able to determine it perturbatively. And the same for the z's. We expect the z's go to 1 in the limit that g goes to 0. And back there, order g corrections. For this particular theory, what we'll find is that these are 0. And so the order g squared are leading corrections. So we're going to sketch how we could determine these parameters and relate this.
You say the zi should go to 1. You're not including g in that, right? Zg, because we don't know anything about that as g goes to 0.
Yes. For zg, we could have other behavior. It will turn out to have the same behavior.
The parameter for 5-4 theory is dimensionless, so we can take higher orders in terms of lambda, but g is not dimensionless, right? So
yes. So to make these formulas work, there's going to also have to be some p dependence. So that's our goal, and we're going to work in perturbation theory. In general, we don't know how to make non-perturbative statements about the relationship to this theory experiment, or work perturbatively throughout today's lecture, and in general, this is usually the best you can do is make perturbative statements.
I didn't quite understand. You said that, so order of G for, why did it vanish for ZG as well? So I know for, yeah, why did the order of G vanish for the interaction Lagrangian as well for ZG?
This term? This is not obvious from anything I said so far. We're going to sketch the computation, and we'll show that this term, this will be from the computation will be later. We'll do enough today to see that this is 0. We won't do enough to determine all the. So we're going to use perturbation theory.
It's obvious because, isn't it? Or
The other two, well, that it has to be 1 at. There has to be a 1 because when ZG goes to 0, we want those terms to vanish.
you said that you're gonna prove for all three, but I'm saying that
The 1 is clear for Z phi and ZM. It's not necessarily clear for Z.
Couldn't you just add the interaction term in the counter term Lagrangian and then do the same thing that we did with the free Lagrangian, and then we would have the same constraint?
so that's basically
Well, what we know is that when G goes to 0, we should just get an overall, this overall coefficient of this term should be 0, but it's already 0.
Yes. Okay, yeah.
Rini?
I have a question on why. What is the physical meaning of that term?
Of what?
I can understand how to think about the other terms, but the last term I don't know how to think about it. The why.
The y. Okay, so let's write down the Feynman rules for this theory, and we can see what each of these terms represent. So in our naive theory, we just have a single vertex, which is 3-point vertex in position space. The rule for this is IG equal d4y. Once we shift and rescale, we still have a 3-point vertex, but the coefficient is now ICG equal d4y. But not only do we have this vertex, we have 2 other vertices. We have this y5 vertex, and there's 2 different terms here, but both of these terms are quadratic in the field, so we can represent them with the same vertex. So the y phi term is a vertex with 1 field. So it's a vertex with 1 line going into that. This is really weird. We try to interpret the Feynman diagrams. It's like particle just disappears or appears without interacting with anything. So this is really strange. But nevertheless, the formal Feynman rules we developed have no problem treating a term just 1 field. And so the rule for this is y integral d4y. And this last term, the last vertex we have, is a vertex with 2 lines coming out because there's 2 fields in this term. There's also 2 fields in this term. This term is we can write down easily in position space. This term, because it has derivatives, it's much easier to write down in momentum space. This in moment. Up here, this is position space. Here, I'll write down the rule in momentum space. We also have a vertex like this momentum P going into and out of the vertex. The rule for this is I minus 1 minus CM m squared. So it's a longer Feynman rule, but it's just it's a vertex with two lines coming.
Is it a mix and match like position and momentum space rules? Like wouldn't we have to do some sort of like, I don't know, like Fourier transform before like putting them all together?
Yes, we will, and we'll do that.
Okay.
We're first going to study some objects where this one doesn't play a role, and we'll work in position space. Then later we'll use all three of them.
The momentum space rule is for the correlation function, or is it for the S matrix?
The rules for the vertex are the same for the correlation function and for the S matrix. What changes is which diagrams we consider and how we treat the external lines. But the rules for the vertex are the same. Okay. So let's start by using one thing that we assumed to try to get some handle on how what these parameters are and train them. Let's start by looking at one of the consequences of the LSE assumptions. Okay. In particular, we assumed that the phi acting on the vacuum was asymptotically one particle state, which implied that the vacuum expectation value of the field should be 0. So let's see what this constraint, this assumption, this is one of our assumptions, or a consequence of one of our assumptions in the LSZ reduction formula. See what this tells us about our parameters. So if we want to write down, if we want to compute this using Feynman diagrams, we can do that. So there's one diagram I can draw where I just use this vertex. And this vertex has a contribution at order G. It also contributes at higher order in G. In general, Y will be some series which has a first non-zero term at order G, but there also be right terms. So this term is order G. Also, at order G, I can draw a diagram using this vertex. And the coefficient of this vertex has a G, it also has a ZG. ZG is 1 plus something higher order. So this term will also contribute at order G. It has additional contributions at higher order, but it has a contribution at order G. And anything else I write down will involve more vertices at the higher order. So if I'm working at order G, this is the all there is. And in fact, there's nothing else I can write down that's order G squared. I can't, no diagrams that involve 2 of these vertices or 2 of these vertices or 1 of these each.
Wait, so were we saying that all of these sum together equal 0 because of our assumption from before?
That's right.
Okay.
Why is the first diagram in order G?
Okay, so let's write down the analytic expression for these diagrams. So this first diagram, I'm going to call my internal point Z. So we're we're computing a correlation function in position space, Heisenberg picture. So we replace the lines with propagators. This has a delta x z. It also has one vertex, and so we should use. I called it z. This Feynman rule. We get a factor of I y integral for z delta x z. So this part comes from the vertex. This is from the line, and there's no symmetry. So this is order G because y is order G.
Why is y order G?
Y has to be order G. It can't be order 1 because we know that when we take the limit G goes to 0, we should get back to the frequent Gordon theory. So with this, we write y is some coefficients n. We know the series has to start at 1. Power 1, because otherwise arm won't go away.
Excuse me. Why is the next term supposed to be of order G to Q, not the second problem?
Well, this term is order G cubed because I need to use at least 2 more vertices to write down a next order contribution. The next terms I can write down something like this, or this. So this term has 3 G's and 3 powers of ZG. So this is an order cubed diagram. This has 2 G's, 2 of the ZGG diagrams. This is like ZGG squared y, which is order cubed. And this is okay. So this is this term. The next term is, we can again use the Feynman rules. We have this time 2 lines. So we get 2 Feynman propagators, delta x z and a delta z z, and 1 vertex. It's the 3.3 line vertex. So we get a I z g integral RC plus order terms. Okay, so we can factorize this.
Sorry, do we not have another factor of G, like I, Z, G, G?
Yes, thank you. Okay, we can factorize this expression because delta ZZ is independent of Z. This is translation invariant, so we can shift it. Same as the Feynman propagator from 0 to 0. This is independent. So we can factorize it and write this as IY plus I CG G, and the Feynman propagator evaluated at 0 times this integral. So if we want this to be 0, it should be 0. This prefactor should be 0. So we should have this is equal to 0. That tells us that y is equal minus G times the Feynman propagator at 0. But the Feynman propagator at 0 is the integral.
That side of the blackboard is not.
Not very good. Okay. Is that better? Thank you for pointing that out. Before, okay. I, and the exponential goes to 0. This is I e to the I 0 over p squared minus m squared by epsilon. This term goes away. So it's just 1. I mix up k and p. Okay, so this parameter y has to be this. We want the vacuum expectation value to be 0. And this is related to the Feynman propagator at 0, which we look at this integral. Perhaps not so surprising. We won't analyze it very carefully now, but if we did analyze this more carefully, we could show that this integral diverges. Perhaps not so surprising from a dimensional analysis point of view. If we could go to spherical coordinates, which we can in a sense that we'll see in later courses, this integral will be like p cubed dp over p squared for large p. We would expect that it diverges for large p. So this diverges. That was not a very careful argument. You can make it careful and show that this diverges. But this is nothing new for us. We've seen divergent intermediate quantities many times in this course. This is just like the ground state energy. This is just like the divergence we saw in non-relativistic quantum mechanics scattering. This is nothing new. We can't observe this directly. This is a tool we use to calculate our observations. So we know what to do by now. We introduce a regulator, do our computations, and at the end, get rid of our regulator. We can do the same thing here. I won't go through all the details, but exactly the same procedure works. Nothing new here. This diverges, but not observable. And in fact, we can see what the end result has to be for this case. So what this is saying is that the sum of these diagrams vanishes. We did that by showing that basically this part of the diagram is going over here by x factored out. We factored out this part. And that works more generally. We didn't need to use the fact that x was an external point. If x was an internal point, connect this to some other part of the diagram, the same factorization would work. So this cancellation will work not just for diagrams like this that are where x is an external point, it also works for x being an internal point. In this class of diagrams that are connected to something else just by a single point are sometimes called tadpole diagrams. And so what this is saying is that tadpole diagrams cancel. That's the consequence of this assumption. We could go through and introduce a regulator, calculate everything. What the net effect of that would just be cancellation.
We should say that sum of all tadpole diagrams.
Yes, absolutely. Thank you for pointing that out. That's all. Yes.
So when we have a divergence, when we compute the Casimir effect, and or the ground state of the Hamiltonian, you get infinity, and the regulator is a physical thing that makes sense. You can't have infinitely high modes and stuff like that. Here, the divergence comes from it's not a physical ground. Like y only appears because we insist on using perturbation theory, using the LSD reduction formula. So I don't understand where you can get a regulator that lets you get rid of that divergence.
Well, so what this the fact that this diverges is saying that this diagram that diverges and this diagram diverge. But what we're measuring when we're measuring some scattering process is never an individual Feynman diagram. It's always a sum. Anytime this diagram shows up, this diagram is also showing up. And what we're physically measuring will be only related to a sum of those diagrams. So in that sense, it's the same. It's something we can't measure this separately from this. And
just add infinities, say okay to cancellation.
it's exactly the same thing we've been doing the entire course. Casimir effect in the tutorial yesterday.
Do we say that the sum cancel or that they will cancel each other at each order?
At each order they cancel. Yes. So it's an even stronger statement. That's a stronger statement. Irene?
Is this a statement we make, like we demand this, or it occurs? Because YP will come from the shift in the LSZ formula. So it's not something arbitrary, it's very definite.
Yes, so we made this assumption. This assumption tells us something about how our perturbation theory tells us about
So
the parameters.
the assumption in the first place that it creates XY.
That's right. Our assumptions tell us we had to introduce y, but y had to cancel out of our calculations. Yes.
Could you go over how you're getting rid of? So is the statement that y has to be 0, or is the statement that y diverges?
Y diverges. The statement is that this diagram, which is proportional to y, diverges. This diagram is proportional to zg and this Feynman propagator at 0 also diverges. The sum of them is 0. To make that statement mathematically precise, we'd have to introduce a regulator, then compute the sum, then remove the regulator. We've done that, so I won't do that explicitly. We'll do it explicitly in future courses, but
is this how to call it, one point function being 0 a new assumption, or is that?
This is so remember when we were checking our assumptions for the LSZ formula, we assumed that phi acting on the ground state was 0. Was a one particle state at plus or minus infinity. That can only be true if so one particle states are orthogonal to the vacuum. So if that's true, then this is translation invariant. So if this is 0 at plus or minus infinity, it has to be 0 at all times. So this followed from the assumption that phi of x and t at acting on omega was a one particle state at t goes to plus minus infinity.
I thought that I understood, but now I don't.
Okay.
We have said that y is a power series in G, and that its first term is 0, but at the same time we say that that series is divergent.
Yes. So we're saying we're saying C0 is 0 and C1 is infinity. Right. Yes. It's strange, but it's the same thing we've seen before.
Can I ask one more question?
Yes.
Why is the conclusion that it's fine because it's not observable and not we can't use the LSE reduction forms?
Well, if there weren't experiments to arbitrate between those two choices, maybe you could debate that. But we can compute things using the LSZ reduction formula, and it works. So there is an active area of research of trying to make everything we've done mathematically consistent. That's a very hard problem, and there are many open questions there. Yes, so you're right to So to be skeptical and ask questions, but unfortunately, for many of these things, nobody knows the answer. So we have to resort to physical argument. Okay. Okay, so we saw consequence of one of our assumptions for the LSZ reduction formula. Let's look at other one. We assume that the form factor was e to the I kx.
Just to be clear, we haven't made any new assumptions up to now, right?
No, we haven't. So LSE, we also assume this. This is a weird equation to analyze using Feynman diagrams. It's a mix of position space and momentum space. So we're not going to work in a hybrid position and momentum space. Let's work in either position or momentum space. There's two ways we could do that. So we can define I'll write it like this. This to be the 2-point function of just x minus y. I can also define a Fourier transform of this. And because of the translation invariances, Fourier transform will only depend on a single variable, not two. Physically, that's basically because this propagator will conserve momentum. And so we can write this, I get the definition right, to P as we can do two things. We can write this as Q P and P prime. So you just take a Fourier transform with respect to x and y of G2 of minus y. But we can also write this as just a delta times some G2 of P. Okay. So these are the natural objects we can compute using Feynman diagrams. They're the position space correlation function or its Fourier transform with a delta pulled out. And to connect these objects to experiments, we can use an exact result. And I alluded to this yesterday. It's known as the Lemon spectral representation. And this is an exact result, and it relies on a few assumptions. So to derive this result, we need to assume, at least in the form I'll present it to you, is that the vacuum expectation value of the field vanishes. This is a familiar assumption. We've talked about this before. We also need to assume that the form factor is e to the ikx. Again, something we've talked about many times. So far, these two assumptions are nothing new. They're just the same as consequences of our LSC reduction formulas. We're going to make a third assumption, which is that there are no bound states. It's possible to slightly weaken this assumption, but the simplest version of the statement assumes this. Before I sketch an argument of why this, what the result is and why it's true, let's take a break. During the break, Irina had a question about what I mean by a bound state. So let's think classically for a minute. So if we have two particles and they're at rest relative to one another, then the total energy of that two particle system is at least twice the mass of those two particles if they're at rest relative to another. They could also have some extra kinetic energy if they're moving away from each other or moving relative to each other. It's also possible that those particles are interacting. So there might be some energy that that are attractive or repulsive force. If there's a repulsive force, then the energy of having the two particles close together will be greater than 2m. On the other hand, if there's a bound state, there'll be some attractive force between those two particles, and we can have a state that has energy of less than 2m. And that's what I mean by a bound state, even in the quantum system. A bound state is a state of two particles that has an energy of less than 2m. So this is a two or more particle state. With E less than 2m. Okay. So so I claim there's an exact statement we can make about the two-point function with these assumptions. And the way to do that is to basically insert the resolution of the identity inside the two-point correlation. So we can write the identity operator in quantum field theory. This one we can do perturbation theory as a projection operator onto the ground state plus a projection operator onto the one particle states. At least if we sum over all possible momenta. Plus a projection operator onto the multi-particle states. I could group the one and multi-particle states together. I'm going to separate them out because they're going to have a different role in our final result. So for these multi-particle states, Ek represents the total energy of that state. K represents the total 3 momentum. And in general, I need additional parameters to fully describe the state. This could be parameters like relative momenta. Depending on the system, there might be additional or particle number, total particle number. And depending on the system, there might be additional parameters we need to describe the multi-particle state. I'll just collectively indicate all of the other information we need besides the total 3 momentum to specify the state as sigma. And so sigma might have some continuous or discrete part, so we should sum or integrate over all of the multi-particles. So this is saying that the vacuum plus the one particle states plus the multi-particle states span our space.
Why don't the one particle states have extra variables like sigma?
If I tell you the momentum of a one particle state, I've fully specified the state. at least for scalar.
Isn't the same thing true for multi-particle states?
If I tell you that the total 3 momentum of a 2-particle state is k, I still don't know the relative motion of the particle.
So the k's are the total momentum.
This is total, yes.
Okay.
Okay, so let's insert this identity into our 2-point function. Let's assume that x naught is greater than y naught, so it's already time ordered.
Sorry, why did you say other parameters instead, but for sigma instead of other modes or other particles? What, is it more general than saying other particles?
Well, so here I'm summing over 2 particle states and 3 particle states. So there's one and n particle states. So there's a discrete parameter here that tells me how many particles are in the state.
So there's one parameter talking about other particles. Why is it called?
It's a collection of parameters, but if I have a 2-particle state and I know the total 3 momentum, that's not enough to fully specify the state. I need a relative momentum.
Okay, but
And if I have a 3-particle state, I need 2 relative momentum. The total 3 momentum and total energy will play a special role. That's why I singled those out. There's a whole bunch of other parameters. Well, at least 2 other parameters, depending on, you could generalize this to particles with spin or other, or charge or characteristics, in which case there might be extra parameters. Sigma. Okay. So if I plug this identity in here, I'm going to put the identity right here in between 5x and 5y, assuming it's time ordered, so I can forget about this for now. I get 3 terms. Omega 5x, 5y. I get a second term, which is 2 integrals. And I get a third term, which is very similar to the last term, but it involves the multi-particle states. Sorry, I have too many integrals here. One integral there. Yes. Okay. So I have 3 terms here. One of these terms is very easy to deal with. Which one? The first one. Yes. Yes. Exciting. Yeah. This term's 0 by assumption. So that term goes away. This term, we know how to calculate as well. So this k pi omega just becomes a e to the I k dot I minus x. This is exactly the same term found in the calculation of the free two-point function, with one difference, is that the energy here is the physical energy. We didn't need to use the Lagrangian at any point. So this term, plus the term with the other time ordering, can do exactly the same manipulations we did when we computed the free two-point function, and we'll get a term it's the same as the free propagator, just with physical mass instead of Lagrangian mass. We didn't need to use the Lagrangian. So this term leads to basically this with m going down physical. We also have a new term here. And this new term contains information about how a one particle state, or at least a field operator acting in the vacuum, overlaps with multi-particle states. This contains information about the overlap of the field operator in the vacuum with the multi-particle states. And in particular, we can use something, say, where this extra term has support in momentum space. We can use our result from before when we rewrote the measure in a Lorentz invariant method. This integral, our motivation for writing it down like this was we wanted to have something that was Lorentz invariant, and we argued that we start with a Lorentz invariant, manifestly Lorentz invariant measure, put in a delta, and put in a step function. We get that measure. So this works for a multi-particle state if this m is the invariant mass of the n particle state. In other words, if ek squared minus k squared is m squared, we can take this difference of the energy squared and the total energy squared and the total 3 momentum squared for a multi-particle state. That's a Lorentz invariant quantity. We call the invariant mass of that state. And so we can do the same thing for these terms. So in particular, this tells us that these terms have no support in momentum space in the region where Ek is less than 2m. So the fact that you're assuming there's no bound states means that if we plot Ek versus k, there's a state, the ground state, which has no energy and no momentum, so one particle state, which total momentum has mass m. If total momentum is 0, the energy is m, and they're bound states. Now, bound states live up here, there's a gap. So that tells us that this term has no support in momentum space. There's no overlap. There's a gap between the one particle state attribution, the two-point function of the one particle state and the multi-particle states. So the result, I'm skipping a few steps here. The result is that the Fourier transform of the two-point function has a term that's like the free propagator, and it has another term which looks like the free propagator. But it has this extra factor rho, and rho contains just these deltas. So there's no overlap between this term and this term. There's a pole here where k squared is m physical squared. And this integral over S runs over the region. This term encapsulates the multiparticle states. So S is basically the allowed invariant masses of the multiparticle states squared. So there's no overlap between where the denominator here vanishes or where the denominator vanishes. And rho of S explicitly is just some deltas, some an integral over sigma, these deltas. And we also have what's left over after we try to translate these away. So the important feature of this is this term is exactly the same as the free theory. And there's some extra stuff coming from the multiparticle states. But the key feature is that the exact propagator has a pole at the physical mass. And with residue I.
Sorry? I didn't quite understand how you came up with G sub 2. G2K. The whole thing.
The whole thing? Okay, I skipped a bunch of steps here. This part. Okay, so what would we do if we were going to calculate the free propagator? We would take these field expressions, field operators, and use the relation with the creation and annihilation operators.
Yeah.
You get two integrals. Well, let's do that. I'll be explicit. So we're going to calculate 0, 5x, 5y. We're not doing the time ordering, we're just doing this. This is d3k pi cubed, 2ek, d3p, 2 pi cubed, 2ep, 0. Then we have a e to the minus I k dot x, ap dagger e to the plus ip dot x. Here. Is that okay? Or you can use the commutator. That will kill an integral. What I'm left with is one integral. And e to the I, we'll set p equal to k. IP dot x minus y. Unless I made a sign mistake, it's the same as we have over here. Maybe I made a sign mistake. The integral e to the ik x minus y. I think I made a sign mistake.
Sorry, what are the bounds on the integral? Infinity, and what's the lower bound?
4m squared. 4m fit. Because there are no states with energy less than 2m by assumption.
But we cannot have any multi-particle state with energy less than 2m, but we can have a one particle state with energy higher than 2m.
Yes, we can.
Overlap somewhat? Or?
It overlaps in just energy, but not in the energy momentum plane.
Okay.
So if a one particle state has lots of energy, it has to have lots of momentum. Okay, so
Sorry, John.
And so I think that will be to the ik dot x, because that's not a 4 vector, right? That's the 3 vector. So if it would have been a minus,
these are
so it is
okay.
ikx for ak and a to the minus ipx.
Okay. Plus. Did I make? I think this is right.
No, that's y.
Right.
One of them is y.
One of them is y. Oh.
The second one is y.
Second one is y.
And still not right, I think.
Okay, sign mistake somewhere. I want to move on. We can. 4 vector. 4 vector.
Can you explain this energy momentum thought process?
If I have a 0 particle state, it has to have 0 momentum and 0 energy. If I have a 1 particle state, it can have 0 momentum and energy m. I can boost that so it has more energy and more momentum. If I have a 2 particle state, well, if the particles at rest relative to another, the energy is 2m, and I can boost that. But I can also have a 2 particle state where there's some relative momentum, so it could have any energy greater than 2m as well.
Can you raise the
Yes. Okay, so this is our exact results. This term came from recognizing our calculation gave us one term that's the same as the pre-calculation. We get an extra term. I didn't fully show you, but it has an extra delta. So it should be 0 in the region near k squared equals m squared. So when k squared is m squared, this is the most important term. So let's try to compute this perturbatively and see what constraints this result gives us for our parameters. We try to compute G2 of P using perturbation theory. Leading order, we just have a line. There's extra terms. Could have a term like this. There are also terms like this or like this. There are additional terms. We could have a term like this. Have a term like this. Or like this. Or like this. And I may be missing some. There's lots of terms we can draw out this order. Can we say anything about the terms in this line?
Some of them count as tadpoles or no?
Tadpole. So this line vanishes.
Why is the base graph order g squared?
This graph is order 1.
It's okay.
So this is order 1. This is order g squared. This is order g squared as well. These ones cancel. These will be higher order.
Is the cross corresponding to capital Y in the third diagram?
No, the cross, this is the z, phi, and zm term.
I'm sorry, Dan.
Yes?
Where are the Feynman diagrams coming from?
So we're
G2 of P is a 2-point correlation function?
2-point correlation function. If you like, we could write the same diagrams would contribute to G2 of x minus y. And we could take the Fourier transform.
Is that the same thing as that? Is that what you're saying? Like the one we found from the spectrum?
So this is the Fourier transform of the 2-point function using the definitions up here. This is what we computed. This is the Fourier transform of this is the 2-point function. Okay. So there's lots of diagrams here, and we're not going to compute them explicitly. But we can notice something. Notice that the diagrams on the third line look like copies of the diagrams on the first line stitched together. And that's no accident. That's, in fact, a general feature. A very useful way to compute the 2-point function is not to compute all the diagrams individually, but we can think about the structure of perturbation theory. And we don't need to compute all these diagrams. These diagrams we can compute easily by using our knowledge of the diagrams on the first line and stitching them together.
On the third line, isn't the first diagram and the last one?
The same, yes. This is the same. Yeah, I meant to draw this one. So a general diagram contributes to the 2-point correlation function, can be chopped into in an integer number of places. There's one diagram can be chopped in 2 places nowhere. There's also diagrams like this one or this one that if I remove one line will fall into 2 pieces. And we call a part of a diagram that remains connected if you remove any one line, a one-particle irreducible diagram. And so any diagram that contributes to the 2-point function can be has either 0 one-particle irreducible parts, one particle irreducible part, or 2, or some integer number of one-particle irreducible parts. And so to compute correlation function, we don't need to compute all the diagrams. We just need to compute the one-particle irreducible parts and learn how to stitch them together. And let's suppose we know how to compute the one-particle irreducible diagrams. So one particle, to be explicit, one-particle irreducible diagrams will be, first one will be this. Just this part without the lines. I've drawn here an amputated line. Amputated line. This means we're just saying where it connects to the rest of the diagram, but we're not including the line there. There's also this. So that's what I mean by the one particle irreducible parts of diagrams. So if we could compute this, or compute this at some order in perturbation theory, we can use that knowledge to compute the two-point function. Let's suppose we can do that. Let's just call this I sigma of p. If we know that, then the two-point function, the Fourier transform, will just be, we can write that down a expression for that. Its first term, I over p squared minus m squared. The next term, two propagators, both of which have momentum I over p squared minus m squared. And we also have an I sigma of p squared. And so on. This is a geometric series. Every time we add a new 1pi part, we also add a new propagator. This is I p squared minus m squared, I epsilon, geometric series. Let's put a minus sign. So we can sum the series, and we'll get the exact result is I, or all orders result, I over p squared minus m squared, I epsilon, and 1 over 1 minus sigma of p. Which is I over and so this makes precise what I was saying yesterday when I said that the corrections shift the mass. We see that by resumming these diagrams, these corrections shift the mass. If we compare this expression we got from doing perturbation theory to all orders and resumming it to this expression, we get some constraints on sigma of p. So if we want I over p squared minus m squared minus sigma of p squared is I epsilon, I have a hole at p squared physical squared. Well, we need to know two things. We need to know the relationship between m squared, mass in the Lagrangian, and m physical squared. And that also put a constraint on sigma evaluated at m squared. So we need to make another assumption. Let's make the assumption. We assume m squared, m physical squared. The choice. Make that choice. Relate our experiment to our formulation of the theory. Then Chalin-Lemon representation tells us that if there's a pole at p squared plus m squared, we should have that sigma of m squared is 0, so that the pole is not shifted. If we want the residue to be at the right place, residue to have the correct value, then we should have that sigma prime m physical squared. And so these two these two conditions provide us 2 extra constraints on our parameters, or 3 if we count this. We determined how to relate m to experiment, and these two at leading order will determine zm and z phi. Higher orders the constraints will mix. So we're almost finished. Related nearly all of our parameters to experiment or to some general features, quantum field theory. And what's left is the coupling constant, G. Yes.
Sigma prime here, it's a derivative with respect to
Sigma prime. This sigma prime of m squared means the derivative of sigma of p squared with respect to p squared evaluated at m squared.
derivative with respect to p squared.
Yeah, this is the sigma of p squared.
Here we had like we added 2 numbers, the z and the y.
Mhm.
In a more general case, if instead of being phi 3, it were like phi 7, we should have added more terms.
Yes.
And how do we know that those 2 conditions are enough to fix everything?
They're not. We need one more condition. So we can count their conditions and our parameters. So we started off with 3 z's, y, m, and g. And we have a condition here. We made an extra assumption. We assumed m squared is m physical squared. 1 constraint. We have these 2 constraints that gives us 2 more. And we also had one from the tadpoles, the y here. So that's enough to determine m for 4 of the parameters. We haven't said anything about zg or g. Yes.
The spectrum formula has a component that's like I over k squared minus s plus I epsilon. The delta shifts the pole away from k equals plus or minus is.
Yes. So.
I mean s.
Yes. So this integral is only from 4m squared to s, and there's deltas s minus m squared. So this term is 0 near, or not 0, but not non-singular. It has no. The denominator is never 0 in a region near k squared equals m physical squared. So there's an isolated pole here.
Thank you.
Okay. So we need one more condition. One more condition and one more definition. And that comes from considering the vertex. What we did in tutorial yesterday is we defined our coupling by saying that it's some particular observable, it's the transmission coefficient, evaluated at some particular energy scale, E equals mu, had some particular relationship to the coupling constant. We could do that. One choice could choose the set f as I to be equal to some particular function of g for some particular fixed given I and f. In principle, that would work. It turns out to be more difficult to do in practice. Instead, what we do, what we'll see and we'll do explicitly in future courses, is we'll do something analogous to this. So a general 3-point diagram has the following structure. It has a 1pi part in the middle and some connected parts on the edges. So imposing a condition on FSI would be composing condition on some of diagrams of this form. Just like 1pi diagrams are the building blocks of the 2-point function, if we know this 1pi part, we can compute the exact 2-point function. We don't need to compute all the diagrams separately. Just the 1pi part is enough to reconstruct it. In the same sense, although there's more going on in the 3-point function, it's not just a geometric series. By the same reasoning, if we know the 1pi 3-point function, we have in principle enough to compute any 3-point correlation function or any scattering or decay rate that involves just one particle going to two particles. So in practice, what we do is we impose a condition on the 3-point irreducible function. And so we'll demand that function evaluated at some reference momenta is equal to g. Just like you saw in tutorial, there's many equivalent ways to define a theory. So this could define a reference momenta to be such that p1 ref squared with the p2 ref squared is equal to mu squared. We define that coupling constant to be related to some observable or something we could use to build observables at a reference energy. There's some ambiguity in doing that. There are a class of theories we could get that describe the same physics. And we could define the same, we could get the same theory by imposing this condition at different energy scales. So, general, the coupling constants will become energy dependent. And there'll be some functions, curves, g of mu, as functions of mu that describe the same theory. So any 2 points on this curve be the same theory. And any 2 different curves represent different theories.
Sorry, Dan, what's our reference momentum, like P ref?
It's the momentum at which we use to relate the coupling constant to something we can observe. So this is how we're going to formulate our theory. This is something that we could either observe directly or a building block that we can construct our observable. This is a building block of So we'll go through this in much more detail and be more explicit and determine functions. This is where we're going. Okay. So our time in this course is just about at an end. There's many things I didn't get a chance to talk about, and some I only got to talk about very briefly. So this topic of renormalization is something we'll discuss much more in QFT1 and with Gong and in QFT2. Also, in this course, we restricted ourselves to spin zero particles. So Gong's going to tell you a lot more about what happens when we have particles with spin or fields that transform non-trivially under Lorentz transformations in QFT1. Many other topics and applications that we'll explore later in the year, including gauge symmetries in QFT1 and 2. Completely different way to think about field theory using path and functional integrals in QFT2. CFT and anomalies and quantum fields and strings, and in a number of many other courses, including quantum matter and cosmology and quantum gravity and particle physics, you'll explore applications of this. So thank you all for your attention and all of your questions. It's been a pleasure to teach you.